Hi, you guys. How are you? So what we're going to do is, for the first thing, I don't know why all these things keep coming open and out. They're driving me a little batty. Okay, so I want to talk about, we have the fundamental theorem of calculus part one, and then there's a fundamental theorem of calculus part two, which is pretty cool. So we're going to talk about what those things are as soon as we go on. So over here, this is the graph of f. It got cut off. So you're looking at the graph of f. Okay, this is who it is. And now what I want you to do is, it says the graph of the function f consisting of three line segments is given above. Actually, it's given to the right, where g of x is equal to the antiderivative of f. So let's talk about what that means. So by the way, we know that every derivative has infinitely many antiderivatives. So given that, this is a particular, g of x is some particular antiderivative that's defined as the integral from 1 to x of f of t dt. So before we even begin, if g of x is equal to the antiderivative of f, okay, what does g prime of x equal? If g of x is equal to the antiderivative of f, then what's g prime of x? And let's talk about what that means for a second. So if I take the derivative of g of x, I do get g prime of x, yes? If I take the derivative of this guy over here, the derivative of the integral, right, of x of f of t dt, we should all know that the derivative of the antiderivative is simply the function itself. Okay, so it starts off, and the second fundamental theorem is basically saying that the derivative of the antiderivative just kind of gives you back what you started with. So think about this. If the g of x is equal to the antiderivative of f, well then f must be the derivative of g. Would you agree with that? I hope so. So let's see that. Let me say that again, because I know you guys want to kind of drink that in. If g of x is the antiderivative of f, then f must be the derivative of g. So that means then we know that g prime of x is equal to f of x. And furthermore, if that's true, then g double prime of x must equal, that's right, f prime of x, because we're just taking the derivative of both sides. So before we've even answered any questions below, we haven't even answered anything yet, this integral right here has basically established the relationship between g and f, where g of x is an antiderivative of f. Right? So f is the derivative of g. So again, this integral is basically saying we're talking about one of those antiderivatives that we speak of, because we know that let me say that again, a derivative has infinitely many antiderivatives, and it comes from there. So now it's saying go ahead and compute g of 4 and go and compute g of negative 2. So if I want to compute those two things, I'm going to use this guy right over here. And if you notice on your graph over here, you have line segments, which means they're going to be geometric areas. So we're going to be able to find the areas of those things. So I want to get this out of the way because it's kind of in my way, because we need a little better room to do some of the nice stuff that we are doing. Okay, so I'm going to ask you guys that as we go along, I'm going to hit pause on this, and as I hit pause, I want you guys to go and do the work and then kind of hit play again to see what's going on, because I'm going to do the same thing. So I want to find out what g of 4 is equal. Whoops, go back to your pen, Char. G of 4, okay, that's because x is now 4, is equal to the area under the curve from 1 to 4 of f of t dt. So that is how it is defined. So it's basically saying on this particular antiderivative that we speak of, if you want to find out what the value of g of 4 is, which is our original function, you have to find the area under the curve from 1 to 4 of f of t dt. So I'm going from 1 to 4, so I'm going from here to here. So I have to find this area here, so to speak. And if I look, I already know, just to save myself some time, that these two net areas are going to cancel each other out. So technically, I just need to find the area of that trapezoid, and let's see if I can do it in my head. So 4 and 1 is 5, right? Yes, 4 and 1 is 5, because those are my two heights, times 1, so this is equal to 5 halves. So therefore, if I were to graph g of x on my original function, I would know that g of 4 is equal to 2.5. So I'm just going to put this off to the side, that g of 4 is equal to 2.5, to save myself a little bit of trouble, okay? And then you want to find out what g of 2 is. So g of negative 2. And g of negative 2 is equal to the integral from 1 to negative 2 of f of t dt. And if you remember your rules for integrals, you always want this lower limit to be the smaller of the two. So I would go ahead and reverse it and do it from here to here. So it's the area, the opposite of the area under the curve from -2 to +1. So that means I'm finding the area of this guy right over here. So that's technically the area of a triangle, but it's going to be the negative of that because I'm kind of going in the opposite direction. And if I'm right, this is a 3 by 4, which is 12, so that's going to be equal to 6. So g of -6. So g of -2 is equal to -6. If at any time my numbers are wrong, call me out the next day. I'm totally okay with that because I'm just kind of trying to fly over here. But I think it is a 3 by 4, and that would give me -6. Okay, so now we know that we can go ahead and these questions, by the way, should feel really familiar to us because the beauty of it is the more we keep adding on, the more definitive we start to become with our answers to our questions. So for example, it says find the instantaneous rate of change of g, right? So you want to find the instantaneous rate of change of g, which means you're looking for g, you got it, g prime with respect to x at x equals 1. So now let's put our clever hats on. So we know that g prime of 1 is equal to f of 1 because we defined that over here. So that means that all I have to do is look on this graph because this is a graph of f which is equal to a graph of g prime. So therefore g prime of 1 is the same thing as f of 1, and f of 1 is equal to 4. Done. So that was what the question, this is a conceptual question, is can you establish a relationship between f and g in this problem, which we did at the very beginning. Okay, now part C, and this is all, it just all kind of ties in together, which is why I really enjoy these problems. It says to find the absolute minimum value of g on your closed interval. If you're looking for your absolute minimum, that means you should be looking at either two things, and you should hit pause and talk to your neighbor and say, neighbor, I think this is what she's looking for. Okay, pause. Okay, so we've paused. Kind of paused. And the thing is if we're looking for absolute mins or absolute maxes for that matter, you always check your endpoints and your critical numbers. Okay, so your endpoints, we already have them. So these are my two endpoints right here. And then our critical numbers where it would be an absolute minimum. Okay, so, and if you think about it, if you're like, well, I can actually conceptually do this, well, you know, I love that. Okay, you know, I'm going to eat it up. So, and if you said the absolute minimum is going to be right over here at -6, -6 is going to be our absolute minimum, I 100% agree with you for two reasons. Number one, we don't have any relative minimums because we actually have a relative maximum at 3 because your slope goes from positive to negative, right? So it's doing all of this increasing because we know when we're looking at a graph of the derivative, because this is the derivative graph, anytime we're above the x-axis, we're increasing. We're doing all of this increasing and then this teeny tiny amount of decreasing. So that means then at -2, it starts way down and then it increases, 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 and then just decreases and never makes its way back down to -2. So if you looked at it that way, it's gorgeous. I love that you did that. From a mathematical standpoint, you could actually say that, you know, there's no other places that it's going to be crossing the x-axis because technically if it was going to be a minimum, it would have to go something like that where it goes from negative to positive, okay? So now for part D, it's saying the second derivative of g is not defined at x equals 1 and 2, which we could all see that over here. How many of these values are points of inflection on the graph of g? So again, remember, we're looking at the graph of f prime, of g prime, which is our first derivative. So we're looking at a first derivative graph, yes? So that means the slopes on this graph are your second derivatives. So I hope you said, like if I asked you where is it concave up, I hope you say from the interval from here to here because your slope is positive, and then you're concave down all along here with the exception of that guy because the second derivative doesn't exist there. So if it's saying which one of these are points of inflection are where we have changes in concavity. And we're going from concave up to concave down, so the only one that it applies to is at x equals 1 because your second derivative is negative here and your second derivative is still negative on either side of 2, so therefore it is not going to be a point of inflection. Okay? I want to get started on another problem, and I have about 5 minutes left on this video for me to show you that. So I'm going to kind of get you started, but again, it's more like the applications of that second fundamental theorem we spoke of. Okay? So I'm going to kind of half-assed it there, and I'll be right back. Okay. Hi, everybody. So I'm going to kind of jump down to part D. I'm going to request that you guys go through um, A, B, and C on your own. It's good practice for you. But I want to talk about how we would evaluate f of -3 and f of 4. And if you go back to the original problem, I'm hoping that this pen works, you guys. Give me a luck. Wish me luck. Oh, it is. It's good. Okay. And if you go back up here, it says first of all, you're looking at a graph of f prime, and let f be a function defined on the closed interval from -3 to +4, where f of 0 equals 3. So now I want to find out what f of -3 is and what f of 4 is. So here's where your fundamental theorem of calculus gets to come into play, and we get to be clever. So I want to figure out what f of -3 is. So the thing is I have a graph of f prime in front of me. So what that means then, I know that f of 0 is equal to 3, so I know that, like, I want to set up my integral. So I have, my integral from, oops, am I running off the paper? The integral from a to b, of f prime of x dx is equal to f of b minus f of a, right? So that's the first fundamental theorem of calculus, which we know. So now when you decide who you're picking for a and b, well, I know this is going to be my lower dude, and -3 is going to be my upper dude, if you will. So, in which I'll make my adjustments as needed. So, but if you look at this, the integral from 0 to -3 of f prime of x, right, is equal to the negative of -3 to 0, because again, we don't like to reverse, we like to have our lower limit as our lower limit. So this is going to be equal to, I'm sorry, I'm cutting into the paper, negative parentheses, so I'm just going to my negative sign. So that's going to be f of 0 minus f of -3, right? So if you look over at this guy, so here's what I want you to look at. I want to go back up to, and that's where I kind of butchered this, but I didn't. If you look at your first fundamental theorem of calculus here, right, which we know, if you think about it, in my mind, I see 3 variables. I see the area under the curve, and I see my final minus my initial. So I see 3 variables. So if you look at this equation, which I'm so annoyed with myself, I kind of butchered words because it's writing right into the paper because it's such a big thing. I have the negative of -3 to 0 of f prime of x is equal to negative f of 0 minus f of -3. And I'm looking for f of -3 because that's what it asked me to find. I know what f of 0 is, and then I can find the area under the curve to the x-axis, area under the curve from 0 to -3. So it's basically finding this area here and then this guy right over here. So, and if I find that, then I can figure out, what I need to do for these particular problems. So to me, I want you to look at your fundamental theorem of calculus, this beautiful thing right here, is almost looking at it as 3 variables. So you could set it up the same exact way for f of 4. So you would just do the integral from 0 to 4 of f prime of x dx equals f of 4 minus f of 0. And again, you're looking for f of 4. You know what f of 0 is, and you can certainly find the area under the curve from 0 to 4 because that's what it's asking you to find, which would be this guy right here, which would be the rectangle minus the semicircle, if you will. So I'm going to leave it up to you guys to find out what those are. But I just want to get you guys into the habit of taking a look at these kinds of problems, because in that big packet that I handed out to you guys last week, there are a couple of problems that are like this that I think do make an appearance. And I actually think I might throw one in there at you just to make you take a look at it. So look at this video, and then test out the other problems, and then we'll definitely fill in the blanks on Wednesday. Okay? I'll see you guys soon.